Hey guys, welcome to our new lecture. In this lecture, we'll learn Kőnig theorem and Tutte theorem. There are 4 parts in this lecture: Kőnig theorem, Tutte theorem, and 2 corollaries of Tutte theorem, Peterson's corollary and Bird's corollary. Okay, the first theorem is Kőnig theorem. If G is a bipartite graph, then the maximum size of a matching in G equals the minimum size of a vertex cover of G. This is a minimax relation theorem. It states equality between the answers to a minimum problem and a maximum problem. Like in this result, the maximum matching and the minimum cover have the same size. The prerequisite is G is a bipartite graph. Here below we have 2 graphs. The first one is C5, which is not a bipartite graph. The second one is a bipartite graph. We can find out maximum matchings in both graphs. We can find a matching with 2 edges in C5, and this is a largest matching. In the right graph, we can also find a largest matching with 2 edges. It's easy to see that there is no perfect matching. There is no matching with 3 edges. On the other hand, a minimum cover of C5 has 3 vertices. 1, 2, 3. We need at least 3 vertices to cover all the edges, because each vertex can cover 2 edges. And C5 contains 5 edges, so we need at least 3 vertices to cover C5. In the right bipartite graph, we can find a vertex cover with 2 elements. Every edge has 1 end in either this vertex or this vertex. So in this graph, the maximum size of a matching equals the minimum size of a vertex cover. Kőnig theorem tells us that this property holds for all bipartite graphs. Actually, it's easy to see that the size of a minimum cover is greater than or equal to the size of a maximum matching. We have proved this result, which is tau G greater than or equal to nu G. Because a vertex cover needs to cover every edge of the graph, so it covers every edge in the matching. That is, every edge has at least 1 endpoint in the vertex cover. So we have tau G greater than or equal to nu G. This is the first step of the proof. We have already seen that a minimum cover has at least the size of a maximum matching. That is, tau G is greater than or equal to nu G. Now take a minimum vertex cover U of G. We construct a matching of size U. To prove that equality can always be achieved, that is, to prove tau g equals nu g. Given a minimum vertex cover, it remains to find a maximum matching with the same size. Here is the cover U. It has some vertices in A and some vertices in B. We let R denote the intersection of U and A, and let T denote the intersection of U and B. Though the other part of A is A minus R, and the other part of B is B minus T. All these are just notations to make the problem clearer. There are some edges from A minus R to T, and some edges from R to B minus T, and some edges from R to T. But there is no edge from A minus R to B minus T. There is no edge from A minus R to B minus T. Why? Because U is a vertex cover. If there is an edge from A minus R to B minus T, this edge should have one endpoint in the cover U, which is a contradiction. Now we consider the subgraph induced by R and B minus T, denoted by H, and the subgraph induced by A minus R and T, denoted by H prime. Note that the union of H and H prime does not contain every edge of G. But that does not matter. We can find a matching covering R in H, and we can find a matching covering T in H prime. The two graphs, H and H prime, are disjoint, though the two matchings together form a matching of G, which has the same size of U. This is our proof idea. Here is the formal proof of step 2. Consider two subgraphs. Let R equals U intersection A and T equals U intersection B. Let H prime be the subgraphs of G. H is induced by R union B minus T, and H prime is induced by T union A minus R. We will use Hall's theorem to show that H has a matching covering R and H prime has a matching covering T. Since these subgraphs are disjoint, the two matchings together form a matching of size U in G. So we consider why these two graphs satisfy Hall's condition. This is the last step of our proof. Each subgraph satisfies Hall's condition. Since R union T is a vertex cover, G has no edge from B minus T to A minus R. Suppose S is a subset of R, and consider the neighborhood of S in H, NHS, which is a subset of B minus T. If for every S, we have that the size of NHS is greater than or equal to the size of S, this is Hall's condition. Our proof is done. If not, suppose that the size of NHS is less than the size of S. Then we can substitute NHS for S and obtain a smaller vertex cover. since NHS covers all edges incident to S that are not covered by T. Let's take this graph for an example. If there is a vertex set S such that the neighborhood of S, NHS, has smaller vertices than S, then we can use NHS to substitute S to get a smaller vertex cover. This vertex, this vertex, and this vertex form a smaller cover. But U is already the cover with the minimum size. According to the given condition, U is a minimum cover. The minimality of U thus implies that Hall's condition holds in H, and hence H has a matching covering R. We can apply the same argument to H prime, which yields the rest of the matching. The two matchings can form a bigger matching satisfying the condition. Let's come to the second part, which is Tutte's theorem. Hall's theorem considers matchings in bipartite graphs, but Tutte's theorem considers matchings in general graphs. There is only one definition here, which is QG. Given a graph G, let QG denote the number of its odd components, that is, the ones of odd order. An odd component is a component which has an odd number of vertices. An even component is a component which has an even number of vertices. Note that an even component is totally different with an even graph. An even component is a component whose size is even, and an even graph is a graph in which every vertex has even degree. The graph below is not the graph G. It is a matching in the graph G. The graph G minus S has 4 components. Every component is a connected component, so we should draw more edges to make every component to be a connected component. This component has 3 vertices, so this is an odd component. So is this one, 3 vertices, odd component. And this component has 7 vertices, so this is an odd component. The last component has 4 vertices, so this is an even component. Note that this is an even component, but this is not an even graph. An even graph is a graph such that every vertex has even degree. So we have totally 3 odd components. So here we have QG equals 3. This component should also be connected. Here is Tutte's theorem. A graph G has a perfect matching if and only if QG minus S is less than or equal to the size of S for all the subsets S of VG. Let's take a look at the figure below. If we delete this S, we have 5 odd components left. 1, 2, 3, 4, 5. 5 components. Every component has 5 vertices. So we have 5 odd components. Qg minus S equals 5. And the size of S is 3. 5 is greater than 3. So by Tutte's theorem, this graph has no perfect matching. To see a graph has no perfect matching, we need only to find an S such that Qg minus S is greater than the size of S. But if we want to prove G has a perfect matching, by Tutte's theorem, we have to prove that Qg minus S is less than or equal to the size of S for all subsize S of Vg. In fact, it's easy to prove the necessity. G has a perfect matching. Why should Qg minus S be less than or equal to the size of S? Again, let's take the following graph as an example. This component has 5 vertices. To construct a perfect matching, we have 2 edges and at least 1 edge between this component and S is needed. We need at least 1 edge between S and this component. For the same reason, a matching in this component can cover at most 4 vertices, so we need to send an edge to S to get a perfect matching. This component, we need to send an edge to S to get a perfect matching, and this component, we need to send an edge to S. This component, we need to send an edge to S. So we have sent 5 vertices to S. Because the edges in the matching are disjoint, S should have at least 5 vertices. For general graphs, the number of odd components Qg minus S should be less than or equal to S for every subset S. This is the formal proof of necessity. If G has a perfect matching, then clearly Qg minus S is less than or equal to the size of S for all S contained in Vg. Since every odd component of G minus S will send an edge of the matching to S, and each such edge covers a different vertex in S. This is a matching, so all the edges in the matching should have different ends. This is the necessity. Now we come to prove the sufficiency. If Qg minus S is less than or equal to the size of S for all S contained in Vg, then G has a perfect matching. Tutte's condition is preserved by addition of edges. If G prime is obtained from G by adding 1 edge E, and S is contained in Vg, then we have Q G prime minus S is less than or equal to Q G minus S. That means the number of odd components does not increase. This is because when the addition of E combines two components of G minus S into one, the number of odd components does not increase. If we add one edge E, whose ends are in the same component, this new graph is called G prime, then QG prime minus S equals QG minus S. The number of odd components does not change. If we add one edge E whose ends are in different components, then QG minus S is less than QG minus S, or equal to QG minus S. In any case, the number of odd components does not increase. One odd and one even together become one odd component. Two even components become one even component, and two odd components also become one even component. So the addition of E combines two components of G minus E into one. The number of odd components does not increase. To prove G has a perfect matching, suppose to the contrary that G contains no perfect matching. If we add one edge to G, the new graph has no perfect matching. Then we add the edge to create a new graph G prime. If we go on adding one edge to G prime, the new graph has no perfect matching. Then we will add the edge to create a new graph G double prime. We can continue this procedure to get a new graph until adding any edge to this new graph will create a perfect matching. Then we stop. This is to say, there exists a graph G prime satisfies the condition, that is, QG prime minus S is less than or equal to the set of S, has no perfect matching, but adding any edge to G prime creates a perfect matching. Adding any edge to G prime creates a perfect matching. We can always find such a graph G prime. Actually, the order of G is even. From the condition, we see that it holds for all subsets S. So if S is an empty set, then QG minus S equals QG equals 0 because S is an empty set. That means the graph G itself has no odd components. Every component has even vertices, so we have the size of G is even. If we keep adding edges to G, we will get a complete graph of even order. Any complete graph with even order has a perfect matching. So G prime is a subgraph of a complete graph of even order, and a supergraph of G, such a G prime, must exist. We will obtain a contradiction in every case by constructing a perfect matching in G prime. G prime has no perfect matching, but we can find a perfect matching. This contradiction implies that our assumption is false. G contains a perfect matching. This is what we will do in the next step. This is the third step of the proof. The size of G is even. Consider a simple graph G such that G satisfies the condition, has no perfect matching, but adding any edge to G creates a perfect matching. Note that here we continue to use G to represent this graph instead of using G prime. This is just for convenience. By considering S equals empty site, G minus S is G. We know that G has an even number of vertices, since a graph of odd order must have a component of odd order. Now we come to the next step. Let U be the site vertices in G that are connected to all other vertices. That is to say, every vertex of U has degree n-1. Note that maybe there is no such vertex with degree n-1. Then U is an empty site. The following discussion still holds. Now we let U be the site vertices whose degree is n-1. Suppose G minus U consists of disjoint complete graphs. G minus U consists of disjoint complete graphs. This is case 1. If G minus U has a component which is not complete, we consider it as case 2. Here, we consider only case 1, the case that G minus U consists of disjoint complete graphs. We build a perfect matching for such a G. The vertices in each component of G minus U can be paired up arbitrarily with one left over in the odd components. Since QG minus U is less than or equal to the size of U and each vertex of U is adjacent to all of G minus U, we can match these leftover vertices arbitrarily to vertices in U to complete a matching. Let us consider the first case through this graph. The first case is every vertex of S is adjacent to every other vertex. So every vertex of S is adjacent to every other vertex. And many edges. And every component of G minus S is a complete graph. Every component is a complete graph. The black edges exist in each component. In each component, we can find such black edges because each component is a complete graph. And the black edges between S and G minus S, such an edge, such an edge, such an edge, exist because every vertex of S is adjacent to every vertex of G minus S. We see that the black edges form a perfect matching. This case is too special. There are so many edges, so it's easy to find a perfect matching. The next case is G minus U is not a disjoint union of cliques, of complete graphs. At least one component is not complete. We can therefore find two vertices in the same component which are not adjacent. For example, X and A are not adjacent. Then there is a shortest path from X to A. We can find a shortest path from X to A. Then we let this vertex be Y, the neighbor of X on the path, and this vertex be Z, the neighbor of Y on the path. We see that X and Z are not adjacent because if there is an edge XZ, then we can find a shorter path from X to A, a shorter path XZ and following the path to A. But XYZ following the path to A is already a shortest path. So we say that on a shortest path between them, there are two non-adjacent vertices XZ at distance 2, which have a common neighbor Y. Furthermore, G minus U has another vertex W, which is not adjacent to Y. We can find another vertex W, which is not adjacent to Y. Why does such a W exist? Because by the definition of U, U is a set of vertices that are connected to all other vertices. If Y is adjacent to every other vertex, then Y belongs to U. But now, Y is in G minus U. Y doesn't belong to U. That means there is a vertex that is not adjacent to Y. So we can find a W such that Y and W are not adjacent. Note that Y and W may be in different components. Maybe not, both okay. We know that G has no perfect matching, but adding any edge to G will have a perfect matching. By the maximality of G, adding any edge to G produces a perfect matching. If we add the edge XZ to G, it has a perfect matching denoted by M1. If we add the edge YW to G, it has a perfect matching denoted by M2. Let M1 and M2 be perfect matchings in G union the edge XZ and G union the edge YW respectively. It suffices to show that in M1 union M2, we will find a perfect matching, avoiding XZ and YW, because that would be contained in G. We see that M1 is not a perfect matching of G because the edge XZ is not in G. Also, M2 is not a perfect matching of G because the edge YW is not in G. But we want to find a perfect matching avoiding the two edges. xz and yw. This is what we want to do next. Let f be the graph on Vg with the edges that belong to exactly one of M1 and M2. In the graph below, let these black edges be the matching M1. The 6 black edges is a matching M1. Let's draw another perfect matching M2 by red edges. M2. We see that the red edges also form a perfect matching. This is M2. F is the graph with the edges that belong to only one of M1 and M2. These edges are both in M1 and M2, so they do not belong to F. These edges are either in M1 or in M2, but not both, so they belong to F. So we can draw F like this. Now this is the graph F with 12 vertices and 6 edges. Note that F contains the edge xz and the edge yw. Because the edge xz is in M1 but not in M2, and the edge yw is in M2 but not in M1, then F contains xz and yw. Since every vertex of G has degree 1 in each of M1 and M2, so every vertex of G has degree 0 or 2 in F. We see that these 6 vertices have degree 0 in F, and these 6 vertices have degree 2 in F. Hence, F is a collection of disjoint even cycles, alternating between edges of M1 and M2 and isolated vertices. Here F contains a cycle of length 6. F contains no odd cycle because the edges are alternating between M1 and M2. This edge is in M1 and this edge is in M2, M1, M2, M1, M2. So it's an even cycle. If xz is on this cycle and yw is not on this cycle, then we can use the edges of M2 on this cycle and the edges of M1 outside this cycle to form a perfect matching in G. Let's repeat it again. Let C be the cycle of F containing xz. If C does not also contain yw, then the desired matching consists of the edges of M2 from C and all of M1 not in C. This matching avoids xz and yw, so it is a perfect matching in G. If a cycle C contains both yw and xz, then we can also obtain a matching of VC using only edges of G. That means avoiding both xz and yw. We will find such a matching, use the edge xy or the edge yz. Note that we have already known xyz is a path of length 2. This is the cycle. on which we can find both the edge xz and the edge yw. Because both xy and yz are edges in G, this has been confirmed at the beginning of this case. We can use some edges of M1 and some edges of M2 to find a perfect matching. Here in this graph, the matching contains the edge YZ, one edge from M1 and two edges from M2. We see that the red edges form a perfect matching in this graph, and it avoids to use the edge xz and the edge yw. So how to find such a matching in a general cycle? We use yx if the distance between y and x in C is odd, and we use yz otherwise, then the distance between y and z in C is odd. Here in this graph, the distance between y and z on the cycle is 1, 2, 3. So we use yz. And the distance between y and x on this cycle is 1, 2, 3, 4. So we don't use the edge xy. In this illustration, the second case applies. Then the remaining vertices of C form two paths of even order. We use the edges of M1 in one of these paths and the edges of M2 in the other to produce a matching in C that does not use the edge xz or yw. That is to say, we can use some edges of M1 and some edges of M2 to form a new matching, avoiding xz and yw. Outside C, every edge of M1 or M2 is in G, so combined with M1 or M2 outside C, we have a perfect matching of G. Tutte theorem is proved. We have two corollaries of Tutte theorem. The first one is Peterson's corollary. This result was found by Peterson in 1891, long before the Tutte theorem, but it can be viewed as a corollary of Tutte theorem. It says that every three-regular graph with no cut edge has a perfect matching. For any subset S of Vg, let H be an odd component of G minus S. This is an odd component. The number of edges between H and S cannot be 1. If there's only one edge between H and S, then this edge is a cut edge, but G has no cut edge. So the number of edges between H and S cannot be 1. Also, the number of edges between H and S cannot be even, cannot be 2. Why? Because this is a three-regular graph. Every vertex has degree 3, and H is an odd component. It has odd number of vertices in H. If the number of edges between H and S is even, then the subgraph H, the total degree here is odd, which is impossible. The order of H is odd, and every vertex has degree 3. but the degree sum of H should be even. So the number of edges between C and H, between S and H, should be odd. It cannot be 2, it cannot be 0. That means there are at least 3 edges between H and S. Let's repeat it again. Let H be an odd component of G minus S. The number of edges between S and H cannot be 1, since G has no cut edge. It also cannot be even, since otherwise the sum of the vertex degrees in H would be odd. Hence, there are at least 3 edges from H to S. Since G is 3 regular, each vertex of S is incident to at most 3 edges between S and G minus S. This is because every vertex has 3 incident edges. Now let's consider the number of edges between S and G minus S. We consider the number of edges between S and G minus S. So we are calculating the size of this set. It contains all the edges between S and G minus S. It is less than or equal to 3 times the size of S because every vertex of S has at most 3 edges outside to G minus S. So it is less than or equal to 3 times the size of S. Also, it is greater than or equal to 3 times Q G minus S. This is because we have proved that between every odd component and S, there are at least 3 edges. There are totally Q G minus S odd components, and each component has at least 3 edges sending to S. So there are at least 3 times Q edges between S and G minus S. So we have 3 times QG minus S is less than or equal to 3 times S. So we have QG minus S is less than or equal to the size of S, which proves the corollary. By Tutte's theorem, it has a perfect matching. The condition that the graph has no cut edge is necessary. This condition cannot be deleted. The graph below is a 3 regular graph, but it has cut edges. It has 3 cut edges. And this graph has no perfect matching. Deleting the central vertex leaves 3 odd components. 1, 2, 3. 3 odd components. From Tutte's theorem, we see that it has no perfect matching. The second corollary of Tutte's theorem is Birch's corollary. Birch wrote the second graph theory book in history. This result says that the largest matching in an n-vertex graph G covers n plus the minimum of the size of S minus QG minus S for all S contained in VG vertices. It is called a defect version of Tutte's theorem. The proof technical is to construct a new graph G' which satisfies Tutte's condition. Thus, G' contains a perfect matching. From this, we can find a largest matching with the desired size in G. This is the first step of the proof. We construct some new notations. Note that when S is an empty set, the size of S is 0. So S minus QG minus S equals 0 minus QG minus S is less than or equal to 0. Thus, we have the minimum size of this parameter for all S contained in Vg is less than or equal to 0. We let ds equals Qg minus S minus the size of S, and d equals the maximum number among all ds for S contained in V. D equals maximum ds, thus minus d equals minimum minus ds for all S contained in V. Minus ds equals S minus QGS. So we see here n plus this parameter. This parameter is minus d, so this is minus d. So we need to prove that the largest matching in an n-vertex graph G covers n minus d vertices. Here we cite some new notations. All the notations are only for convenience. Let's take an example. In this graph, let S be a subset with 3 vertices here. If we delete this S, the number of odd components is 5. 1, 2, 3, 4, 5. So Qg minus S equals 5. Thus, the size of S minus Qg minus S equals 3 minus 5 is minus 2. We can check that for any S of Vg, for any subset S of Vg, the minimum number of the size of S minus Qg minus S is actually minus 2. So the largest matching in this graph, by Burge's corollary, it covers at most n minus 2 vertices. The largest matching cannot cover all the vertices. At least 2 vertices cannot be covered. Why? Here in this example, to find a largest matching, in each odd component, we can find at least 2 edges in the matching. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So there are now 10 edges in the matching. But it's not a largest matching because we can find more edges. Here we have 1 edge. Here we have 1 edge. Here we have 1 edge. This is the largest matching. Now we see that this vertex and this vertex are not covered by the matching. So it covers n minus 2 vertices. This is the formal proof of step 2 to find the upper bound. Given a subset S of Vg, at most S edges can match vertices of S to vertices in odd components of G minus S. Like in this example, there are 3 vertices, so it can match at most 3 odd components. So there are at least 2 odd components cannot be matched. So every matching has at least QG minus S unmatched vertices. This is the upper bound. Then we will prove that we can get the upper bound. We will get the upper bound by using Tutte's theorem. To use Tutte's theorem, we need to construct a new graph. This is the proof of step 3. We have shown that no matching can have more than n-d vertices. This is the upper bound. We want to achieve this bound. Considering the case S equals empty set shows that D is non-negative. Now let G prime, a new graph, be obtained by adding a set of D vertices to G, each of which is adjacent to every other vertex. Like in this example, we will add 2 vertices, and each of them is adjacent to every other vertex. It's adjacent to every other vertex. Okay, you know what I'm going to do next. We need to join the 2 vertices to every other vertex. Now we prove that the new graph G prime satisfies Tutte's condition. That is, the condition QG prime minus S prime is less than or equal to the set of S prime always holds. We distinguish 2 cases. The first case is S prime is an empty set. The second case is S prime is not an empty set. This is the proof of step 4. To prove QG prime minus S prime is less than or equal to the set of S prime for S prime equals empty set. For each S, ds equals QG minus S has the same parity as G. That is, if G is even, then ds is even. If G is odd, then ds is odd. ds and G have the same parity. Why? Let's see the graph below. G has a subset S, some even components and some odd components. If we delete all the even components, then the remaining graph and G have the same parity because we have deleted even number of vertices. We see that there are some odd components. In each component, it has odd number of vertices. So, if the number of odd components is odd, then the total number of vertices in the odd components is odd. If the number of odd components is even, then the total number of vertices in the odd components is even. So the number of these vertices and this number QG minus S, which is the number of odd components, they have the same parity. So QG minus S plus S has the same parity with G. So QG minus S minus S has the same parity as G. It holds for every subset S. Thus we have D equals maximum ds has the same parity as G. Therefore, we have the result that the set of G prime equals the set of G plus D is even. If D equals 0, that means for every subset S of Vg, we have Qg minus S is less than or equal to the set of S. That means the graph G satisfies Todd's condition and the proof is done. If D is greater than or equal to 1, that means we have added some vertices to G to form a new graph G prime, and every vertex of D is adjacent to every other vertex. So G prime is connected. So G prime itself is a connected component with even vertices. So Qg prime minus S prime equals 0. It is less than or equal to the set of S prime. This condition holds for S prime equals empty set. What if S prime is not empty set? This is step 5, the final step. We need to prove that Qg prime minus S prime is less than or equal to the size of S prime for S prime not an empty set. In this case, we have two subcases. Subcase 1, if S prime is non-empty but does not contain all of D, does not contain all of the new vertices, then G prime minus S prime still has some vertices from D, and the vertices in D have the property that every vertex is adjacent to every other vertex in the whole graph. So G prime minus S prime has only one component, and 1 is less than or equal to the size of S prime. Because S prime is not an empty set, it has at least one element. The second subcase, subcase 2, is S prime contains all the vertices of D if D is contained in S prime. Let S equals S prime minus D. So we have G prime minus S prime equals G prime minus D minus S. So it equals G minus S. So Qg prime minus S prime equals Qg minus S, because all the new vertices have been deleted. Qg minus S is less than or equal to the set of S plus D equals the set of S prime. So from here we see that G prime satisfies Todd's condition. Because G prime satisfies Todd's condition, we can find a perfect matching in G prime. Then we can delete the D vertices from G prime to get G again, so we can obtain a matching of the desired size in G. Because deleting D eliminates edges that match at most D vertices of G. Now we have Burge's corollary. Thanks for watching this video. See you next time.